Our next section deals with trigonometric integrals. So these are going to be integrals whose integrands consist entirely of trig functions. And so we'll kind of start out with some, as it says here, simple strategies, and we'll work towards more complex, both functions and powers of functions. So to start out with, substitution and multiplying by 1 are some simple strategies. So taking a look at this integral, right, tangent isn't something that we know from a table or something like that. So what we have to do is kind of look for something that's equal to tangent that's maybe a little easier to deal with. One relationship that we know for tangent is that the tangent of x is equal to the sine of x over the cosine of x. And so this is going to be our solution for being able to integrate this guy. Because now we have the top of a fraction, the bottom of a fraction, right? We can consider the denominator to be the inside of our function for u substitution. So we'll let u be equal to the cosine of x. So du will be negative sine of x dx. And so by multiplying both sides by negative 1, we end up with our numerator being equal to negative du. And so we have this u substitution we can use. And we then know that we have the logarithm that we're going to use here. So natural log of the absolute value of u. Now we'll put the plus c here. We'll go ahead and swap the u back in. And so we have our solution here will be negative natural log of the absolute value of the cosine of x plus c. For the next one, there's a couple of different options that we have here. Firstly, anytime that we have a radical here, one option that we kind of have is to multiply by sort of an opposing radical. So one thing that we could do here is multiply by 1, and we'll do it in the form of 1 plus cosine of 2 theta. Because we know that multiplying by the conjugate here, it's not the conjugate of the root, but of our binomial, will end us with the difference of squares. And so that's kind of the route that we're trying to go here. And so in the numerator, right, we get both of these guys under the square multiplied together, so 1 minus cosine squared of 2 theta. And the denominator will end up with root 1 plus cosine of 2 theta. Right, in the numerator, 1 minus cosine squared, right, that's going to be sine squared. So we get sine squared of 2 theta under that square root. And so those guys will cancel the square root and the square. And so we get pi fourths to 4 pi thirds sine of 2 theta over 1 plus cosine of 2 theta, and this guy is still under the square root. And the significance here now is that the numerator is going to be some version of the derivative of the denominator. If we look inside that square root and we let u be 1 plus the cosine of 2 theta, then du will be negative 2 sine of 2 theta if we use our chain rule with a d theta on the end. We divide both sides by negative 2, and we get negative 1/2 du is going to be equal to the sine of 2 theta d theta. So we have a negative 1/2 that we're going to end up replacing in here. I'll go ahead and pull that outside first. And so we have du, and we have 1 over root u. And so this is going to be u to the negative 1/2. So we increase the power by 1. That gives us u to the 1/2. That's root u. We divide by the new power. dividing by 1/2 is the same as multiplying by 2. And so we got some cancellation. So we've got negative root u, and u is 1 plus cosine of 2 theta, evaluated from pi fourths to 4 pi thirds. So we go ahead and evaluate cosine of, well, looks like we got 8 pi thirds plus root 1 plus cosine of 4 pi thirds, or sorry, pi fourths times 2 pi halves. All right, so we'll end up with, it looks like 1 plus cosine of 8 pi thirds. Cosine of 8 pi thirds should be, if we look at our unit circle, one way around, that's 6 pi thirds, and then 2 more. So we're looking at a negative there. And then we have 1 plus 0. And so we'll end up with 1 minus root 1/2. And if we want to keep going from here, 1 minus 1 over root 2, that's probably the best way that we can represent our answer here. If we really wish, we can even combine those fractions into a single one using a common denominator, but we'll go ahead and avoid that. And that will be our answer. So if you're looking back here, you can see that we have a cosine of 2 theta. There's probably an alternate method of doing this problem, and I'll go ahead and show that as well. We are going to be using the double angle formula a lot. One such formula here is that the cosine of 2 theta is 1 minus 2 sine squared of theta. And if we go ahead and employ that instead, we will end up making quicker work of this problem. And so we'll be able to cancel out some 1's. So 1 minus 1 plus 2 sine squared of theta d theta. These 1's will cancel. We'll get a root 2 that we can go ahead and pull up front. And the square and square root will cancel. And so we'll end up with sine of theta. And we can then evaluate. Negative cosine of theta evaluated from pi fourths to 4 pi thirds. When we do that, we'll go ahead and pull out the negative as well. Cosine of 4 pi thirds minus the cosine of pi fourths. You can see that 4 pi thirds is going to be down here. So we're still talking about a negative value. And so when we multiply here, we'll end up with negative root 2 over 2 minus 1, plus 1. Root 2 over 2 is the same as 1 over root 2, so we get the same thing again. So definitely some alternate methods. Sometimes you can find ways around doing u substitution by finding a different method. But either way, finding either substitutions that work or multiplying by 1 is a good way for figuring out some trig integrals. We'll go ahead and start looking at some common integrals here and remembering first off maybe where they come from in some cases, and second where we can use them. So it says the following integrals require substituting or multiplying by 1 and then substituting. And so these should be memorized, it says. So these guys are important enough to memorize. The first one we see there is the one that we did back up there, tangent of x. And notice that we have in that first line the answer that we came up with, negative natural log of the absolute value of the cosine of x. If we pull that negative inside, we can actually make it the power on cosine and turn it into a secant. We saw last section what the integral of secant looks like. Right, that was multiplying by secant of x plus tangent of x over secant of x plus tangent of x. And so we get this. And modifications of both of these will give us both cotangent and cosecant. Right, so we're going to have those pop up in some different places, and it would be of great benefit for us to memorize those and be able to recall them instead of having to derive them again each and every time. So with that, we'll go ahead and move on to kind of the meat of this section, is when we start talking about powers of different trig functions. So we'll start out with powers of sine and cosine, and then we'll move on to powers of tangent and secant. So first, we'll go ahead and look at isolated just powers of single trig functions. So looking at sine to the m or cosine to the n, where we have some positive integers. So we'll go ahead and try to see what we can do with the cosine here, cosine to the 5th. So we'll go ahead and think about, what do we know about powers of cosine? What sort of framework do we have to be able to work with powers of cosine? Everything that we have, if we think about maybe some trig identities, right? Everything that we're going to have here, cosine of 2x is to cosine squared of x minus 1. Notice that they're all powers of 2. So what we probably want to do then is turn this into some version of cosine squared of x. This is cosine squared of x squared, but then we kind of have an extra one hanging out here. Right, so if we were to multiply all that back together, it would be cosine to the 5th. Okay, so now we have this cosine squared, and we have a couple of options for what we could do with it. We can maybe use a power reducing. If we do that kind of thing, we're looking at cosine squared of x equals 1 plus cosine of 2x over 2 if we derive from the double angle formula. This does not look like it will be very easy to deal with. We'll have to square it, and we'll have to FOIL on the top, and then we'll end up with a squared double angle there, and that won't be very good. So instead, what we might want to do is look at the Pythagorean identity. Right? Our other option here is cosine squared of x is 1 minus sine squared of x. If we look at it that way, we'll think about how it interacts once we square it. We'll end up with some, we'll end up with a constant. We'll end up with some powers of sine. At the end here, we'll end up with cosine multiplied in, right? And so this could very well act as the catalyst for a u substitution, right? We can make cosine du and make the sine our u. So this definitely looks like the route that we want to take. So we'll go ahead and make that swap. All right. And so what we'll do then is we'll go ahead and do a u substitution. We may as well do it right now. So we'll let u be equal to sine of x, because we have that du then is going to be cosine of x dx. And this will make this integral much easier to handle. 1 minus u squared du. All right, so we can go ahead and square this, FOIL it out. 1 minus 2 u squared plus u to the 4th du. And we can go ahead and integrate. We've got u minus 2/3 u to the third plus 1/5 u to the fifth. Looks like my du broke there. And then plus c. So we'll go ahead and swap our u's for sine of x minus 2/3 sine cubed of x plus 1/5 sine to the fifth of x plus c. Right, and so we think about, why did this work the way it did? It worked the way it did because we were able to sort of split one cosine off and then have an even number left over. And you can imagine then, if the same thing were happening with sine, we would have sine to the fifth, we could break off one sine and then have an even number of sines left over to make this swap. We'd go this way instead. So whenever there's an odd power, we can break one off and make it into some version of du. Turn the rest into the same function using one of the Pythagorean identities, and then work through. So that's whenever there's an odd power by itself. And so next we'll go ahead and look at what happens if there's an even power. Right, if we were to do the same sort of process, we don't have an extra sign lying around to act as a du. So if I were to go through and square all this, I would just end up with a cosine to the fourth of x by itself over at the end, which means that that's not going to be a helpful strategy for us this time. We're going to have to determine something else. So looking at this guy, remember our other option that we kind of looked at was power reducing. So this is our power reducing formula for the sine. And remember, power reducing for the cosine is very similar, but with a plus instead. So when we do that, we'll end up with cosine squared of 2x, which actually does reduce the power. And we can do power reducing again to lower that even further. So that's going to be our strategy for this one. We'll go ahead and turn this into sine squared of x squared dx and use power reducing. So 1 minus cosine of 2x over 2. And we'll go ahead and, since we're going to be doing this a lot, we may as well start writing it kind of to the side here. Let's turn this into a bracket. 1/2 1 minus cosine of 2x squared dx. So we'll square both of these guys. We'll end up with 1/4, and I'll go ahead and take that out. And so we'll have to FOIL this guy. When we do that, we get 1 minus 2 cosine of 2x plus cosine squared of 2x dx. And so what we'll do now is, this guy is good, we can integrate that, no problem. This guy we can integrate, no problem. This guy is too much. We're going to have to use power reducing again. Power reducing, we've got 1/2 1 plus cosine of, this should normally be 2x, but we're starting with a 2x. So if we put 2 in there, we should put 2 in here also. So that should be 2 times 2, or 4x dx. All right, so I'll go ahead and multiply this guy out. So plus 1/2 plus 1/2 cosine of 4x dx. We'll combine some like terms here. We got 1 plus 1/2, that's 3/2, minus 2 cosine of 2x plus 1/2 cosine of 4x dx. And so we'll go ahead and integrate. The nice thing about the power reducing formula is that we always end up with cosines. And what's more, we always end up with cosines just with some coefficient. And so the way that we're going to deal with taking these integrals then is, well, first off, we've got 3/2 x. we're going to keep the same sign. If you're integrating cosine, that's kind of the nicer one to integrate. You don't have to change the sign at all. And the way that we deal with that coefficient in dealing with the chain rule, instead of having to do u substitution every time, that's going to take a load of extra time. Since it's just a coefficient, we'll divide by that coefficient. So cosine of 4x over 2 times 4. We're going to divide by that coefficient. And remember, after you kind of cancel out, do whatever, you should be able to take the derivative of this guy and end up with this guy again. So take the derivative, we get cosine, and then we have to take the derivative of the inside, we get the 2. And so we get, let's go ahead and turn that into parentheses. We don't really need the bracket. 3 halves x minus sine of 2x plus, let's say 1/8 cosine of 4x plus c, and we'll go ahead and just leave it like that. And so that's going to be our strategy then for dealing with an even power on sine or cosine. So we have our sum up statement down here. Integrals involving odd powers of cosine or sine are most easily evaluated by splitting off a single factor. Right? You split off that single factor and use it as your dx. With even powers, we use the power reducing or half angle formulas that we used up here, these guys. All right, so that's the general strategy for dealing with a power of sine or cosine by itself. So now what we'll do is do sine and cosine kind of mixed together. So we're going to do different strategies when we have both sines and cosines kind of mixed together. And so we'll, again, kind of mix these strategies in. We'll figure out how do we deal exactly with these guys. And the idea is we're kind of going to deal similarly with the way that we dealt with even powers of just sine or just cosine. So we'll use power reducing formula on both of these. So this is sine squared. I'll go ahead and actually write that over here, save myself some room. So this is going to be sine squared of x squared cosine squared of x dx. And so we'll go ahead and use power reducing. And so we've got 1 minus cosine of 2x squared. Sorry, that square should go on the outside of the brackets. And then over here, we've got 1/2. Oops, I shouldn't put that in parentheses there. 1/2 1 plus cosine of 2x dx. So we've got 1/2, we'll square it, that's 1/4 times 1/2, that's 1/8. Integral of 1 minus cosine of 2x squared times 1 plus cosine of 2x. And so we are going to have to multiply all this out. All right, so we'll go ahead and start with that squared binomial there. So 1 minus 2 cosine of 2x plus cosine squared of 2x. And then 1 plus cosine of 2x dx. So we'll have to multiply these out as well. And so we'll just kind of do our distribution. 1 times this guy, we've got 1 plus cosine of 2x. Negative 2 cosine 2x times this guy, negative 2 cosine of 2x minus 2 cosine squared of 2x. Right, and then we move on to the cosine squared. So plus cosine squared of 2x plus cosine to the third of 2x. And I don't need that parenthesis. Well, technically I do, but again, I kind of just treat this as a closing parenthesis. All right, and so now we'll combine some like terms. So 1, it looks like minus cosine of 2x, and then minus cosine squared of 2x plus cosine to the third of 2x dx. So we were able to get it down to just these 4 terms, and you can see that we had kind of a mix of these guys, and we had a total of 6 powers amongst them. Now we're down to our highest power is a third power, and we have just cosines. Okay, so now we'll kind of take stock here of what we've got. First off, this guy, these two can be integrated fairly easily. This guy, all it needs is a power reducing. This one is one that's going to need a little bit more attention. So we'll go ahead and kind of split this integral a little bit. So I'll go ahead and do my power reducing here. Right, so minus 1/2, 1 plus cosine of, it already had a 2, so I got to bump that up to 4. Plus, and then that should have a dx, sorry. Plus integral cosine cubed of 2x dx. All right, so we've got 1/8, and that should be multiplied by this whole thing. Sorry. 1 minus cosine of 2x minus 1/2 minus 1/2 cosine of 4x dx. That's that first integral. Plus, and we'll go ahead and start dealing with this. This is a cosine to an odd power. I'll split one off. Cosine squared of 2x times cosine of 2x. So for the first integral, we'll go ahead and combine some like terms. 1 minus 1/2, we get 1/2 minus cosine of 2x minus 1/2 cosine of 4x. And on our second integral, we'll go ahead and use the Pythagorean identity. And we are almost there. So we need to use a u substitution for this second one here. We'll go ahead and make u equal to the sine of 2x. So du will be equal to 2 cosine of 2x dx. And so I'll have to divide by 2 on both sides. And that's my u substitution. Meanwhile, for the first integral, we can go ahead and start working on that. Minus 1/2 sine of 2x. Got to divide by 4. So 1/8 sine of 4x. So that one's done. Now we can go ahead and move on to our u substitution over here. 1 minus, we are turn that into u squared. And then we have to turn this cosine of 2x dx into a 1/2 du. So I'll go ahead and put the 1/2 out there. And so this one's not going to be super tricky. It's just that we've kind of had a lot of stuff to write down, and so we'll have to keep writing it. Plus 1/2 times u minus 1/3 u to the third. I think we're finally ready to put our plus c at the end here. So 1/8 1/2 x minus 1/2 sine of 2x minus 1/8 sine of 4x plus 1/2 u, so that's 1/2 sine of 2x minus 1/6 sine cubed of 2x. If I swap that u in for sine of 2x, and then I multiply it by 1/2. And I think we're good to change this bracket also into a parenthesis. Be very careful though. Technically, these should have parentheses around them. And then this should have like brackets. It's okay if you kind of leave those off, as long as you are clear that this entire 2x goes inside your sign. Hopefully we're okay with that, since we are, in Calc 2. But just in case you are, technically using parentheses around those. And so let's go ahead and finish up. We've got minus 1/2 sine of 2x plus 1/2 sine of 2x. And so it looks like we're about done here. 1/2 x minus 1/8 sine of 4x minus 1/6 sine cubed of 2x plus c. So as you can see, these are going to be the longest of the problems, right? When we have combinations of both signs, and cosines, and you can see that as we kind of work through, we end up doing different sub-problems, right? So we had what was a whole problem just a little bit ago has now become a sub-problem here. So definitely the longest of these are going to be when we have even powers of both sine and cosine going on. So next we'll go ahead and look at what happens if we have a combination of odd and even. If we have odd and even, we'll go ahead and start kind of dealing with it the same way we dealt with it when there was just, say, a sine by itself. Right, so we'll split one of these signs off. And what we would really like to be able to do is make our sine of x some sort of du. So that's our kind of goal, is to get something related to sine of x dx as our du. And so what do we need to do then with this guy? We need to turn, in fact, everything else into cosines. So we'll go ahead and use the Pythagorean identity right here. And that pretty much gets us what we want. We'll go ahead and say, let's let u be equal to cosine of x. And so du would really be negative sine of x dx. And so we're looking at something like this. So we've got integral 1 minus u squared. We've got sine of x dx turns into a negative du. And then lastly, we have cosine to the negative second. That's u to the negative second. And so we'll go ahead and distribute. We've got negative u to the negative second minus, if we multiply these two guys together, we just get 1. And so we can go ahead and integrate, increase the power by 1, divide by that new power. So we'll go ahead and distribute this negative. So we got cancellation here. We just have u to the negative first, and then plus u plus c. So we'll go ahead and put our cosines back in here, but we have a negative first power here. One thing we never want to do is write the 1 over cosine to be the same as cosine inverse, or to the negative first, right? Because this is actually the inverse, right? So we should get our cosine here. So we have to note that this negative first power means inverse function. This negative first power over here means inverse multiple. So we don't want to confuse the two. Inverse multiple, we should actually write this as 1 over u, just so that we can avoid potentially getting those mixed up. So we have 1 over cosine of x plus cosine of x plus c, which would end up giving us secant of x plus cosine of x plus c. So we'll never, ever, ever write cosine with a little negative 1 to mean the multiplicative inverse, because we would just write secant instead. So that negative 1 on any of these trig functions will always mean the inverse function. So please don't get that mixed up. All right, but that brings us to our sum up of the sine and cosine combination stuff. So if both of the powers are even, as it says here, we're going to just use power reducing over and over again until we get everything down to the first power. And so we'll get that longer problem that ends up with a lot of coefficients on the inside. And so we should be able to make quick work once everything's down to that first power using u substitution. If one of the powers is odd, then we could do what we did in this last problem. We split one of the odd bits off, and then that will be du. And then we'll turn everything else using Pythagorean identities into the other function. So the split off one becomes du, and we use Pythagorean identities to change everything else into the form of whatever our u is. Right, and the reason that we're able to do that is, again, because sine and cosine have that relationship where basically the derivative bounces them back and forth between each other, with negatives sometimes added in. But when we go ahead and look at the secant and tangent, we're going to have a different kind of relationship here, since they don't have that nice, easy back and forth, right? Because the derivative of our tangent, derivative of tangent of x is going to be secant squared of x, and the derivative of the secant of x is going to be secant of x tangent of x. So it's not quite the same simplistic back and forth, and you'll see that we have secants no matter what. So we're going to have a little bit different of a strategy when it comes to dealing with powers of secant and tangent. Right, and another thing that we'll have to acknowledge is that instead of having the Pythagorean identity where just adding the squares together of sine and cosine equals 1, right, we'll end up, if we divide everything through by cosine, we get 1 plus tangent squared of x equals secant squared of x, right? And if we move the 1 over, we get the tangent squared of x equals secant squared of x minus 1. So we will need to use both of these and the fact that our derivatives line up this way. And we're going to go ahead and, as it says here, try to discover the strategies. We're going to try to figure out, can we use the strategies that we had here and modify them a little bit using these facts to get our There are reduction formulas. You are not allowed to use them. It's not going to, just memorizing the formula is going to be a lot different from being able to manipulate using these strategies. And that's what we're supposed to be graded on and looking for as far as our curriculum goes. So we are not using these formulas. So be careful when you're looking at the book, the e-text, the interactive content, all that stuff. If they use reduction formulas, you are not to use that. So you can use them on the online homework if you really want. I would suggest not, because that's going to get you in the habit of using them. But technically you can use them. I'm not really grading your work on the online homework. That's just for your practice. That being said, it's better to practice with what you're actually going to use. So I would say don't use the formulas. So we'll go ahead and see what are we able to do with tangent to the 6th, secant to the 4th. So what we liked best back when we were dealing with these sines and cosines is we liked being able to split off a du. We liked being able to split off a du, and furthermore, being able to change everything else into our u. And so if we think about what happens if we try to split off, well, let's take a look at the derivative of secant. Right, derivative of secant is secant tangent. So if we split off a secant of x, tangent of x, we are left with tangent to the 5th of x, secant to the 3rd of x. And I definitely don't have any real good manipulations I can do after that. So we'll go the other route. What happens if we take this guy and we split off a secant squared of x? We're left with tangent to the 6th of x, secant squared of x in our integral. And when we do that, we have an even number of secants. We can turn them into tangents. Right? So we have our du and our u. Remember the relationship. 1 plus tangent squared of x equals secant squared of x. Likewise, secant squared of x minus 1 equals tangent squared of x. So that's the relationship we're going to use here. So we've got secant squared of x. I'll go ahead and write that sort of at the end. So tangent to the 6th of x, secant squared of x, secant squared of x. And we'll go ahead and write the secants as, one of these secants here as tangents. So you've got secant squared of x is 1 plus tangent squared of x. And so now this guy here can become our du. And so our u would be tangent of x. And so we get u to the 6th, 1 plus u squared du. And now this is definitely something we can handle. We got to multiply this guy in, u to the 6th plus u to the 8th. And now it's just a matter of doing the power rule. So we got u to the 7th over 7 plus u to the 9th over 9 plus c. And so now we can just make our swap. U should be equal to tangent of x. And that should do it. So tangent to the 7th of x times 1/7 plus tangent to the 9th of x times 1/9 plus c. And so it was really nice that we had an even number of secants here because we were able to split off the derivative of tangent and turn the rest of them into tangents. So even number of secants, and it didn't really matter how many tangents we had, because we were just going to sort of add whatever was left over. So some number of tangents, even number of secants. That's the strategy that we're going to use there, is we're going to split off that secant squared and go ahead and do our whole du strategy. All right, so the next one we look at then, we're going to modify. We've got an odd number of secants. We have an odd number of secants and an odd number of tangents. So remember the other thing we tried, right, was we took a secant times a tangent off. Oops. If we take a secant times a tangent off, that is the derivative of secant, and we have an even number of tangents left. Since we have an even number of tangents left over, we can turn these into secants. So it's the same kind of idea. So it's secant squared of x minus 1 squared, right, because it's the fourth power. Right, so it's the same kind of idea, just going kind of the other way. So du will be equal to secant of x tangent of x dx. And so u will be equal to, secant of x. And so we can go ahead and just make that swap. U to the sixth, u squared minus 1 squared du. And so from here, we just have to multiply everything out. U to the sixth times u to the fourth minus 2u squared plus 1. So we've got u to the 10th minus 2u to the 8th plus u to the 6th. We do power rules again. Divide by 9 here, 2 ninths u to the 9th plus 1 7th u to the 7 plus c. And then we swap u's back in. So we can make pretty quick work whenever we have either an even number of both or an odd number of both. All right, and so that's going to be our answer. So even number of both, we can split off a secant squared. That's our du. Odd number of both, we split off a secant tangent, and that's our du. All right, so we move on to our last kind of situation. So we have an odd number of secants and an even number of tangents. So we can't split off a secant tangent in this case. We won't have enough secants left over. We can't turn our tangents into secants. And we don't even have a secant squared, right? But if we did try to take it off, if we had say a higher odd number, we wouldn't be able to turn the rest of the secants into tangents. So we're really out of options here. The only thing we can really do is, I suppose we can take that tangent squared of x and turn it into secant squared of x and just see what happens at least. So we got secant cubed of x minus secant of x dx. And so what do we have here? Well, we have seen definitely secant cubed of x, right? We were able to deal with that using this idea. We had integration by parts. Right, so we did that problem already. And we know what the integral of just the secant is. So we know this guy from last section, and we should know this guy from, well, also we had that, up further. Right over here. This guy. So we should be able to employ both of those and basically just come up with the answer. All right, so if we remember from last time, secant cubed of x was 1/2 secant of x tangent of x plus 1/2 natural log of secant of x plus tangent of x. That was the secant cubed. And the secant is just natural log of secant of x plus tangent of x. So if you're tracking along here and you want to memorize, you are going to want to memorize secant cubed of x. To remember what that integral looks like, just remember secant. The derivative of secant is secant of x times tangent of x. The integral of secant is the natural log here. Multiply them both by 1/2 and add them together. That's the integral of secant cubed. All right, and then on the end we have plus c. And we'll go ahead and combine these together. And so we have minus 1/2 natural log of the secant of x plus the tangent of x in absolute values. And so that kind of gives us our strategy last up here. That does significantly limit our ability to deal with this. We don't know how to deal with secant to the 5th, for instance. So we are going to have to limit what we're able to do. But that gives us a pretty good picture of what's possible. So we'll go ahead and sum up here. If we are given a combination of tangents and secants, try splitting off a secant squared. If you are left with an even number of secants, turn them into tangents. This guy will be du, you will be tangent of x. If splitting off secant squared left you with an odd number of secants, you can try splitting off secant and tangent at the same time. If you have an even number of tangents, rewrite those tangents in secants. Same idea, u will be secant, du will be secant tangent. If this didn't work and this didn't work, then you're going to have to rewrite the power of tangent in terms of secant and make a polynomial in secant. As it says here, a reduction formula might be useful. We're not using those, so we are going to be very limited. We can only go up to secant cubed. That's as high as we can go. And that's why I want you to pretty much just memorize that guy, or be able to do it with integration by parts. So we're not going to use the reduction formula. On your homework, go ahead. But again, we don't want to use that on tests. So that's going to end off the section on integrating trig functions. So I'll talk to you guys next time.